Good afternoon, everybody, or good morning, good evening, wherever you are. Welcome to this week's EMinar, and it's absolutely my pleasure to introduce Alison Kirkby, who will be giving us another talk on code. We had one a few weeks ago on time series processing code, Razorback, and today we have a presentation on MTPy. Just to remind you, we've got an exciting series of upcoming webinars, so please look at the list. Next week, we have Doug Olenberg on fundamentals of inversion. That should be very exciting. And then immediately following is Lindsay Higgy, currently down in Berkeley, but shortly moving to UBC, who's basically capturing knowledge in code. She'll talk to us about SimPeg and Geoscience. And then the week after that, we have a fabulous presentation by Constanza Manacero on a very quick approximate way of getting 3D forward solutions in order to do a probabilistic inversion of 3D MT data. Very exciting. And then Juliana Hubert on space weather, GIC's MT. And then another Cody one, NASA Magbell, telling us about ModEM, which I know many of you are using. It's the most used in academic code by far. And then we have Vladimir Puzyarev on EM inversions using neural networks, a whole bunch of inversion type seminars, and Kerry Key on MAR 2D EM that I know a lot of you are using. This does 2D inversion of MT, CSEM, DC resistivity, and borehole EM data. And then Randy Mackey telling us about his codes to do joint inversion. And then we have someone between about, but then we have Malcolm Sambridge, who's last year's AGU Benno Gutenberg medalist and this year's EGU Benno Gutenberg medalist, giving us a very general talk about optimal transport and geophysical inversion. So a whole load of wonderful modeling and inversion talks coming up. Just to remind you that all of these presentations are being recorded and being made available. So you can go on the EMinar's page and you can see the video link and the presentation to past ones, and you can register for upcoming ones. And we've filled out now for all of this year, all of this season, I should say, until late July. And then finally, just to let you know, you're on a Zoom webinar, and you've got some controls. You can control where your audio comes out of. You can send a message using the chat function. Towards the end, when we have a question and answer, if you want to physically speak, you raise your hand and I can allow you to speak. Otherwise, there's the Q&A, and you can send a question at any time, and short questions Alison will answer on the fly. Longer questions she'll answer at the end. So again, we have Alison Kirkby, and Alison joined Geoscience Australia 2008, did a lot of work in geothermal studies, got a PhD in Adelaide, of course, with Graham Hansen. And then since she got a PhD, she's been working in the mineral systems branch, applying MT for a lot of different problems. And we had a wonderful presentation last week showing some of the results of the wonderful work that's been done in Australia. Alison's a developer and user of MTPy software package, and I'll shut up now and hand over to Alison.
Hi there. Hopefully I've appeared on the screen and you can hear me. I'll just start my presentation. So so I'm going to talk about MTPy for MT data analysis and visualization. And I'm speaking on behalf, I guess, of a lot of different people that have been involved in MTPy at various points in the past. So particularly Jared Peacock, who sort of initiated MTPy, but also Faye, who works with us at GA on the development of MTPy, and a whole host of people that have helped at various points in the past, including the MT team at GA. So I'm gonna give you a bit of background on MTPy. I'll then go through the modules, sort of state briefly what each of them does. I'll give you a little bit of an overview of installing MTPy, and then go into a practical demo in the second part of my talk. So showing you some examples of the sort of things that you can do with MTPy. So MTPy was started in around about 2013 at the University of Adelaide. And it was started by Jared, and Lars Krieger was also involved a bit at that time. Back then I sort of got involved a little bit. I added a little bit to MTPy, but I was mainly using it. And then when I came back to GA in 2016, GA commenced development and I became involved a lot more heavily. But GA did a bit of a cleanup of the repository, removing some of the legacy code, adding an integrated testing suite and automated documentation. And we've also done some functionality development, particularly with some of the analysis modules and with the ModEM modules. And generally applying software engineering best practice to the code base. So in 2017, we moved it to a new repository. So this is where it is at the moment, up on the screen. We merged, at that point, there were two versions going in parallel, so we merged those two versions together. And we continue maintenance and development in collaboration with Jared at the USGS. And we're currently just...
What's that, sorry? Your screen. You're not sharing your screen at the moment?
Oh, yes, I'm not. That's a good point. Hold on.
I mean, we're all enjoying looking at you, but maybe we'd like to look at the slides as well, yeah?
Sorry, guys. Can you see now?
Yeah, that's good.
Yeah, we got that fundamental step. Slideshow. There we go. Can you see my slides now?
Yep, it's fine.
Yep, cool. Okay, so I'll continue. So we continue development with Jared at the USGS, and we're also at the moment discussing a possible sort of overhaul of MTPy, moving to a version 2.0, which will have some more sort of fundamental changes to it. So I'll mention that a little bit later on. In terms of access, it's available under an open source software license, so you can use it, anyone can use it. However, as with most open source software, we don't provide a warranty, and if you modify the code, please link to the original. And also we'd appreciate it if you could acknowledge the use of MTPy in publications or wherever you use it. So we've got a couple of publications that you can cite if you use it. And finally, please let us know of any bugs via the issues page, which I'll talk about a little bit later on. So MTPy is a collection of tools to hopefully help you carry out your processing, analysis, modelling and visualisation steps for MTPy, for MT data. But it is a work in progress and it's largely script based. And it's not perfect, it's not complete. There are the odd bugs that we come across. So we do suggest that you kind of understand what you're doing and check your outputs when you're working with MTPy. When you're using MTPy, it is very useful to have some background knowledge of Python to get the most out of it. There's a lot of different resources online. I'm not going to recommend any particular one, but this is just from the Python web page, but there's lots of different resources you can go online and find to learn Python. And it's very helpful, not just for using MTPy, but just generally as a scientist. So I'd highly recommend that. So MTPy is structured around the main analysis steps for MT. So I've got a sort of a diagram up here that was that sort of illustrates the structure, I guess, of MTPy. We've got core processing, analysis, modelling, imaging, and utils. And all of them are kind of interlinked. And this presentation is going to cover most of those modules. Moving forward to MTPy v2.0, we might see a little bit of a structural change, I guess, to MTPy. We haven't really sort of fleshed out how it's going to look, but this is kind of a draft structure that Jared put together. And what we're sort of thinking is, rather than being quite centered around the EDI file, we'll be able to read in sort of a bunch of different types of formats, and they can go in to the MT container. And that will contain standard metadata as well as the actual data itself. And then from there, you can do all of the same things, the analysis and the phase and the dimensionality analysis and phase tensors and everything. And then that can also sit under an MT collection, because often you'll have MT collected in a large survey. And there's all sorts of problems that you run into with like frequencies not lining up properly and that sort of thing. And so having sort of the MT collection will make that step a little bit easier. So that's kind of what we're thinking for a next version of MTPy. But back to as it stands at the moment, I guess the core modules contain basic handling of processed data, reading in of station metadata, conversions from impedance to apparent resistivity and phase and the other way around, reading and writing in EDI files. You can rewrite the data with a change made to the frequency content, for example. And then these will link to the other modules to carry out all the other functions. Analysis covers things like, dimensionality and strike analysis, phase tensors, and that sort of thing. And that links to the other modules. So core, you're reading in the data, and that links to analysis, and then utils to carry out some of the actual kind of processing steps themselves. I'm going to show you a little bit of the analysis, the things you can do in analysis later on. Imaging, as the name suggests, plotting, so individual station plots, maps, sections, that sort of thing, so various types of analysis products and model visualization products. And finally, modelling, which is essentially a wrapper for some of the commonly used inversion codes. So these are the ones that we kind of cover. So we don't actually, MTPy doesn't actually do any of the inversion, but it it creates the inputs for the inversion and then allows you to handle the outputs once you get them out again. And utils kind of covers so a lot of the underlying functionality sits under there. So projections and transformations is one of the big ones, but yeah, just a lot of the kind of grunt work that goes underneath all of the different modules sits in utils. So this is where the repository sits. It's in GitHub, and so this is what the site looks like, I guess. I'm going to step through a few sort of parts of the page that are quite useful if you're starting out. So we've got the issues page, we've got the wiki, and then if you scroll down on the main page, you can get a link to the documentation. So starting with the wiki, so if you click on there, it's got an installation guide. So we've got the most recent one sitting there. So if you click on there, that'll go through in detail how to install MTPy, and I will touch on it briefly a little bit later on, but yeah, that's where you need to go to install it. Documentation, as I mentioned, scroll down on the main page, that will take you to there, and it will show you the documentation, which is sourced directly from the modules. And finally, the issues page. That's the place to go, I guess, if you want to do something and you can't find any example of how to do it. If you think you found a bug, or if you've got a suggestion of things to change in MTPy, that's where you do it in the issues page. So that's what it looks like. And actually, I forgot to mention earlier on in my presentation, but there's actually a MTPy version 2 updates issue, which you can see there. So if you've got any suggestions for things that might be added to the MTPy version 2, then go and put them in that issues page and we'll see it. So installing MTPy. So we recommend installing the Anaconda Python distribution because that contains a lot of the underlying modules that MTPy needs, but it also makes the installation of any other additional modules quite simple and straightforward. So we really recommend that. And you'll need a Git shell as well to interface with GitHub, because I mean, basically, it's a sort of a live Git repository, I guess, and we make updates relatively regularly. So if you install MTPy through a Git shell, you can get the updates pretty quickly. So once you've installed these two, so that the Anaconda and Git, you can then clone the MTPy repository. So Git clone and then the repository, and this is all on the installation page anyway. And then you can install the dependencies. And then to get an updated MTPy, all you have to do is git pull and just do that every day. I recommend doing that every day because we're changing MTPy quite regularly. So that's what I do in the morning. I come in and pull the latest repository. So once you've installed it, you can have a look at the repository itself. We actually have a library of example scripts that I try and maintain to be relatively current. And that sort of, that covers a lot of the things that you might want to do. So if there's something you want to do, check out that scripts directory and see if you can find what you need to do in there. The other spot you can check out is the an MTPy examples workshop, and that's got some examples in there too. Tends not to be quite as current as the scripts directory. I tend to update the scripts directory more often, but those are two spots that you can check out if you want to sort of work out how to do something. Actually running MTPy, so what I would normally use is either a Jupyter notebook or Spider. I use Spider, but there's other development environments that you can use. Jupyter is kind of like a web browser-based notebook where you can either run Python code or you can make comments. So it looks a bit like what I've got up on the screen. And so these actual cells of code you can actually run. So you can sort of step through it, run it on the examples, change it, run it on your own files. If you want to write it to a Python script, you can write it to a Python script, and you can also export to some other formats. So quite useful for demonstration. And I'm going to be showing you the examples in Jupyter sort of format, I guess. But for day-to-day use, I tend to use Spider, which is kind of like I guess it's a MATLAB-like interface for Python, and it's just kind of handy. It's got warnings for syntax errors and stuff, and easy to read the code, and it allows you to store variables so you can kind of inspect them, that sort of thing. So yeah, that's what I tend to use on a normal basis. So installation, if you've got Anaconda installed, it's really easy to install either of those. So Conda install Spider or Jupyter. So before I move on, I'll just sort of speak briefly on Python objects. This is kind of a question I've had before in the past. Like I don't understand these objects and these classes. So I thought I'd just have a quick slide on that. And so a lot of MTPy is it's not just an MTPy thing, it's a Python thing, I guess, or an object-oriented programming thing. Everything's sort of based on objects. So the way you can sort of think about it is you can think of it sort of like an object, like an apple. And so if you were going to make an apple class, the apple would have a color, a width, a height, and then you could do like functions like compute volume, and it's exactly the same with a lot of the MTPy objects. So you read an EDI file into an MT object, and then it has the attributes all stored in there, so latitude, longitude, elevation, and the other standard metadata. Also under the MT object, we have a Z object, so the impedance tensor, and then the tipper object. And then the Z object and sort of the tipper object too, but I'll show you the Z object has a frequency array, and then the data. You've got resistivity, and there's a bunch of other parameters in there that are sort of stored in the object. So it's quite a useful way to sort of interact with the MT data, I guess. Okay, so moving on to some practical use cases. So I guess using some of the AusLAMP data that I've been working with over the last couple of years, I'm going to show you, I guess, a workflow, sort of stepping through from reading and writing an EDI file, some simple analysis tools that you might want to use, plotting an EDI file, penetration depth, data plots, and then inputs and outputs for inversion. So this is the data set I'm going to use. It's from New South Wales and Victoria and Southeast Australia. And if you are interested in the data, you can get the data in the model. So some links are up there. Okay, so reading an EDI file into an object. So first thing you'll want to do is you import the MT module. You define your EDI file, and then you can simply create an object. Once you've got the object, you can see the various different sort of attributes of that object. So it's got a latitude and longitude, easting, northing, so it projects it to easting and northing, and an elevation from the EDI file. You can have a look at the frequency content through the Z attribute. You can have a look at the impedance array, in the error associated with that, and yeah, a bunch of other sort of different things that you can get from the data, the resistivity and phase. In terms of editing data, you can interpolate to different periods. So the example I'm showing here is if you wanted to do interpolate your frequencies to 5 periods per decade. There's actually a function in utils that will create a period list. So you just give it a minimum and a maximum and number of periods per decade. So that's how you create that. And then you just basically feed that into the MT object. So MT object.interpolate and interpolate that onto a new frequency list. And so then you can write those new Z and UTIP objects to a different MT file. And so you'll have a new file with 5 periods per decade. So you can do similar things like, you can do more fancy things, I guess, like if you want to mask according to dimensionality or, or whatever, you can do that relatively easily in MTPy. So dimensionality, which is based on phase tensor ellipses, you need to import the dimensionality object, dimensionality module, and then you can you provided a Z object, which you've just read in, and then a threshold for skew and for the eccentricity of the ellipse, and then it'll give you the dimensionality of your data set, of your file. Strike angle is another one, if you want to calculate the strike angle. It's a similar sort of thing. You provide a skew threshold and an eccentricity threshold, because a strike isn't really defined if your data is 3D or 1D, and then you can calculate the strike. And there's a few other different attributes that you can calculate through in the analysis modules. In terms of plotting, so there's a couple of different plotting options, just making a single sort of EDI plot. So this is a very simple one. You create a plot object, and you provide it some options. So I've got plot num of 1, which I'll just talk about in a second. Plotting the tipper, plotting the not plotting phase tensor, and you can give it a figure size. And so this is plotting the 2 off-diagonal components of the impedance tensor. You can also give it a plot num of 2, which will give you the diagonal components as well. So that's what that sort of plot looks like. Moving on to penetration depth. So we've got kind of functions to do it. Well, we call them 3D, 2D, and 1D. And what it essentially means is 3D is kind of a map view of penetration depth, 2D is a profile, and 1D is at a single site. And so the first one will be 3D. So in this case, you provide a path to your EDI files, and it finds all the EDI files in that particular directory. Provide it with a period to show penetration depth 4. I will actually use my pointer there. And you can choose what sort of mode you want to use to show the penetration depth 4. So in this case, determinant. The other parameter, I guess, which is a little bit obscure, is the p-toll, which is a tolerance around the 100, the period of 100 seconds of which to show data. So if your points are not exactly on 100 seconds, it gives you a sort of a tolerance around that to show penetration depth 4. So if you give it that code, this is the kind of plot that you'll get out. So a bit like this. So you can then, if you want to look at a profile across the survey area, you can do that. So I'll show you the profile across where the grey line is. So next. And so again, you provide this time you provide an EDI list and an EDI path. So I've just chosen that row that I selected before. And you give it some periods to plot. So these are actually periods in seconds. You can choose indices as well, but I'm showing you periods. And then similar sort of input parameters as before. And that will give you a profile, and it's got the penetration depth for those different periods using the Niblet-Bostick transform. And then you can look at a single site if you like as well. So I'll show you that next. So it's simply just provide an EDI file and a file to save to, and it will create a plot, and it will show you the penetration depth as a function of period for the 2 off-diagonal modes in the determinant. Okay, so moving on to phase tensor maps. So you can make phase tensor maps in MTPy. Again, you need to provide an EDI path and a list of EDI files. And so you give the PT, you give the function, I guess, the EDI list, a frequency to plot, figure size, XPAD and YPAD, which is a pad kind of in plot units around the stations, so that you sort of don't clip it right at the data. Plot whether or not to plot tipper. You can give the edge color of the ellipses, the line width of the ellipses, minor ticks, whether to show or not to show the minor ticks, and then what to color the ellipse by. So in this case, I'm going phi min with a range of 0 to 90. And then there's some scaling factors that you sort of need to play around with to get the ellipses sort of the right size. And usually you do need to sort of play around with them a little bit until you get the right size. And you can choose a color map as well to show the ellipses. So that will give you a plot a bit like this. So these are phase tensors for the New South Wales and Victoria data set. You may want to show other data sets with phase tensors, and so you can do that also using MTPy. So in this case, I'm going to show you some gravity data underneath the phase tensor ellipses. And so you've already created in your previous code snippet, you created a phase tensor maps object. So now you don't have to make it again, but you do need to read in the gravity data. So I'm using the NetCDF module to read in the gravity data. It's a NetCDF file, so it's pretty straightforward. You can feed that straight into the object. So you just plot it again, and this time you provide a raster dictionary, which has the data itself, the number of levels to show on the contour map of the data, the color map to show the data with, and there's some titles and some other parameters. And that's the sort of plot that you'll get. So relatively easy to create some sort of overlay plots using MTPy. You can also do phase tensor sections. So I'll show you an example of that here. So I'm just going across the middle of the survey. So this is a phase tensor, how to do a phase tensor section. This time I'm going to colour it by skew angle. And skew seg actually just segments the colour map. So rather than having a smooth colour map, it's going to have steps, so you can kind of see discrete intervals, I guess, in the data. You need to give it the line direction, east-west, so it can order the stations properly. And the stretch is kind of like an aspect ratio of the plot. So that's another thing you sort of need to play around with to get it right for your data. And then again, whether or not to plot the tipper. So you can create that plot, and it'll make you a plot something like this. Yeah. You can also make resistivity and phase pseudo sections. You can make apparent resistivity and phase maps as well. I'm not going to show them here, but there are examples in the examples directory to do that. But for the pseudo section, we've got some similar inputs as before. Give it the line directory, a list of EDI files, and then whether or not to show various different components of the impedance tensor. So in this case, I'm going to just show the off-diagonal components, some resistivity and phase color limits, and then you can choose whether to shift the YX phase into the 0 to 90 quadrant for visualization. And so that's the sort of image that you'll get for a resistivity and phase pseudo section. Okay, so on to inversion inputs. So we can, as I mentioned, MTPy can create inputs for Occam 1D, Occam 2D, the data file for MAR 2D. We haven't tackled the mesh yet. The mesh is a bit more complicated. And ModEm 3D. So we've got quite a few functions to create inputs for and deal with outputs from ModEm. So I'm going to show you Occam 1D and I'll show you ModEm 3D. But again, if you're interested in the other ones, then just check out the examples. Okay, so for Occam 1D, there are 3 input files that you need to create: the data file, the model file with the mesh, so the cell thicknesses, and the startup file, which is kind of a control file. You need to import the Occam 1D module and provide the path to the EDI file. And then you can create the data file. You can choose which mode to invert, so TE, TM, or determinant. And then set some error floors. You can choose whether to remove the phases that are out of quadrant. You can choose whether or not to do that. And that will give you a confirmation that you've written your data file. You can create your model file. So give it a number of layers, a target depth, which is, I guess, the model depth before the padding, and then the bottom layer, which is the total depth including padding, and then the first Z1 layer, so the first layer thickness. And so then you can write the model file. And finally, the startup file, so you just give it the file names to the files you've just created, maximum number of iterations and a target misfit to work towards. So you can write that. So then you've created your inputs, you can go away and run Occam, and then come back and look at the outputs. So I'm going to turn off my pointer. So you need to provide it the model file, the data file, and also the final iteration files that you've just gotten out of Occam. And then you can make a 1D response plot. And so that's just like basically a summary plot. It's got the data and the model response as well as the actual model itself. So resistivity is a function of depth. Moving on to ModEm. ModEm has 3 compulsory input files. It's got a model file, a data file, a covariance file. There are some other files that you can provide, but these are sort of the main ones that are sort of challenging to make, I guess. So I'll step through each of those. We start with the data file. And we start with that because we then build the mesh around the stations. So we need to define where the data is first. And so there are quite a lot of parameters to tweak, and I'm showing you some here, but there's more that I'm not showing you. So you can check out the examples for that. But basically you provide pass-through EDI files, a list of EDI files to invert, and then a period list. So again, I'm just interpolating onto 4 periods per decade, and this example that I'm showing here. And then you can create your data object. So I'm providing it with the EDI list, inversion mode, so what parts of the data to invert, path to save to your period list that you've just made, the type of error floor to set. So in this case, I'm setting it as a percentage of the square root of the 2 off diagonal components, and then a value in percent for that, and then an error type for the tipper, so I'm setting that to 0.01. The final one, the model EPSG code, is quite important. So that defines the projection for your model. So each projection, or sort of, I guess, commonly used projections have EPSG codes associated with them. And so especially when your model crosses UTM zones, it's really important to specify the model EPSG so that the inversion, so that MTPy knows where to project all your stations to. But also you do need to know that UTM EPSG code, because when you're plotting the data later, you'll need to provide it so that it can project your stations again. And so you provide all that information, and then you can write your data file. You can then create the model file. So that, as I mentioned earlier, creates a grid centered on the stations. You can give it a bunch of different parameters. What I'm showing here, we've got cell size in the north and the east direction, number of padding cells. I also, so I've got pad north, pad east, pad Z. You can also specify pad num, which is kind of a number of cells outside the station area before the padding starts to increase. So what I'll do is I'll have the station area, and I'll have, like, maybe in this example 6 cells that are the same width, so 7.5 kilometers, and then we'll start the 7 padding cells after that. So that's typically the way that I'll set them up. So we've got a stretch factor, like for actually in the padding, so vertical and horizontal, number of air layers, a half space resistivity to start the inversion with, a number of layers. So just stepping through, it's probably useful to use a pointer again here. Number of layers, the first layer thickness, and then this is just a method for calculating the padding, and then the target depth. So we're going to 300 kilometers for this inversion before the padding. So you can make the mesh and write the model file. You can then add topography to the model if you like. So that's just simply through the add topography to model function. And then you can write the model file. And so if you decide not to include topography, it's still important to provide bathymetry. So I'll always use this, add topography to model, because it'll add the bathymetry below the surface. So if you just want to add bathymetry, you just give it no air layers. So I'll just go back. You've got this number of air layers. You can just set that to 0, and then it will just put bathymetry below the model grid, in the model grid. Okay, so it'll give you a confirmation that that's been written. Finally, the covariance file, a few less things to sort of think about, I guess, with the covariance file. You can provide it smoothing. You can also give it the number of times to apply smoothing. I haven't shown that in this example here. And you can write the covariance file. Okay, so once you've created the files, it is a good idea to sort of check your input files, open them in a text editor and make sure they look as you expect. But there are a number of different functions you can use to quickly check your mesh as well in MTPy. So you can use the plot response functions, which I'll show you later, to just check the data file before you've even run an inversion. And for the model, you can just check the mesh briefly as well. So plot mesh will just give you this kind of plot. So it just shows you where your stations are, where your mesh is, what your vertical and horizontal mesh looks like. And then the other one that I wrote, which is quite useful, is plot sea level resistivity. And then you can check whether your stations are in the ocean. And this particular grid I'm showing here is a bit coarser than the one I've actually run, but it's kind of, I guess, to illustrate, you know, one of these stations down here is in the sea. So in that case, you would need to, what I basically did is just manually change those cells to land, but you could, you know, you could do that or something else, but you've got to just make sure that your sites are sitting on the land. And I'll just, before I go on to visualizing the outputs, I'll just talk a little bit about ModEm objects, because I actually use the ModEm objects probably more than a lot of things in MTPy. So when you create each of your files, ModEm, it creates an object, and that object has different parameters under it. So if you want to build your own sort of plotting tools on top of that, or if you want to, you know, change resistivity values and write another file, you can do that really easily using the ModEm object. So you can, for example, emobj.res model will give you an array, and that contains your model values, your resistivity model values. So this in this case, if it's just your input model, that'll just be your starting model. But if it's one you've read in from an inversion, that's your inverted model. So I find that really handy to building my own sort of tools on top of that. You've got things like the grid, so the location of the grids, grid nodes, grid north, grid Z, and a bunch of other different things. So I find that really useful to interact with. Similarly, you've got the data object. So you can read it in from a data file, or when you actually create your data file, it will create one automatically. And you can sort of check different, you know, parameters of your data file. Period list, for example. Okay, so visualization of outputs is sort of the last thing that I'm going to talk about today. There are a whole heap of tools to visualize outputs. I'm not going to show you all of them here. I'll show you some of them. So I'll show you plotting depth slices and vertical slices, RMS maps, and some response plots at individual stations. But as with the other things, you can do all of these other ones. There's examples in the examples folder. So to create a depth slice, you need to provide it your model file and your data file names. And then the EPSG, with this particular example I'm going to show you here, you need to provide the EPSG used in projection, because we're actually going to show the model in on a base map. So we're going to project it back to lat longs. A color map, some limits in the resistivity to show on the color map, whether or not to plot the stations on the color bar, some fairly straightforward parameters. So you create a plot slices object. You can then make a plot. And so in this case, I'm going to run a base map plot, and I'm going to plot it at 40 kilometers depth. And so this is the sort of plot that you'll get. So it plots it with a coastline in the background, and so you can see where you are. A couple of things that Jared sort of sent me. He's been working on a kind of a bit more interactive plotting. So that means you can sort of load your model in and slice through all of the different slices and up and down the model, and you sort of, I guess, zoom through the different parts of the model. So that's called Model Manipulator. That's in development at the moment. So hopefully that'll be available pretty soon. There's also Plot Response, which is another interactive tool that Jared's been working on, that it brings up a map and you can click on the station and it will show you the responses for that particular station. But back to the sort of, I guess, the more standard functionality that's there already. There's some functions to plot the response of the model. So you provided with the data file and the response file, and the plot type just tells you the stations to plot, and then the plot style gives you types of, like, how many columns to plot. So I'll show you two of those in the next couple of slides. So in this case, we're plotting plot style of 1, which is 4 columns. And that gives you kind of individual plots for each of your components with the model and the data. One thing that I find quite useful, I guess, for showing in publications is a 1-column plot. So this one kind of puts it all in 1 column, which makes it easy, nice and compact and easier, I guess, to sort of fit into figures. So again, you provide the response in the data file. We just change the plot style to 3, and it will give you a 1-column plot like that. Finally, RMS maps. So it's, I guess, the last example I'm going to show you. So you can create a map of the RMS misfit across the different stations. So the residual file name is what you need to provide, and then a minimum and maximum for the color bar. And then period index of all basically averages the RMS over all periods, but you can choose you know, if individual periods, if you want to see the misfit for individual periods. So that's what that will give you, is a plot with each of the different components showing the misfit. Okay, so those are the examples that I've got, I guess. So in summary, MTPy is a collection of tools to help with analysis and visualization of MT data. And the tools I've shown you include, you know, reading and writing and visualization of MT data, analysis tools, reading, writing, and visualization of inversion inputs and outputs. And so if you have any bugs or if you have any questions, you can have a look at the issues page. And again, you can provide information, provide any ideas for version 2.0 of MTPy under the issues page as well. Thank you. That's all I've got.
Well, thank you very much, Alison. Absolutely wonderful, and I'm sure I'm clapping on behalf of all the attendees. So, Alison will be very happy to answer questions, and they're starting to roll in. I'll read out the question, Alison, so it gets onto the recording, and then yeah, you can answer it. So the first question from Talia Avilés. Sorry if I'm not pronouncing your name correctly. When is created the grid on the Z direction, is there an option to vary the grid size along this direction?
Yes, there is. This is in the ModEM object, I'm assuming. Yeah, you can. You can. So the default, I guess, is that it will it basically increases in a logarithmic. So it starts with a Z1 layer of whatever you provide, and it will increase it logarithmically down to your maximum depth. But you can just kind of override that. You can redefine your Z mesh however you want, if you want to do that in Python. So and then write it out to a new file. So I guess those are your options. Hope that answers that.
Yeah, and Jade Crosby says, great talk, Alison. I was wondering why, when using ModEM, you interpolated the frequencies before inverting. Why not use the original data frequencies? And I think this is an important point. You talked about interpolation, and you have to be a bit careful that, you know, if you're interpreting the real and imaginary parts separately, that there might no longer be Hilbert transform pairs, right? So I'm always a bit scared about interpolation. Yeah,
I mean, I guess for me, the data that I've been using was not collected on that, like the sites are not all on the same frequencies. And so for running the ModEM inversion, it's less efficient if you try and if you have like all of the different frequencies that were there's, you know, sort of twice, or I think maybe even more than twice the number of frequencies that you have to invert for. And so, yeah, it's just, I guess it's an efficiency thing. That's why we interpolate.
Yeah, certainly when you have a heterogeneous data set, you have to do something like that. Otherwise, you're going to spend a lot of time. How do you do the interpolation? Is it are you fitting some sort of spline function to the real and imaginary parts separately, or how does
I'd have to double check that, but I think it's just a linear and log space. I think once we tried to do splines, it just causes problems if you've got spikes. So yeah, I think it was just a linear in the end, but I can double check that.
Okay. A simple question now from Farid Smai. Does MTPy, can it write EDI files?
Yeah, it can. Yeah. Yeah, there's examples how to do that.
Raha Hafizi, does MTPy have the option for showing the dimensionalities in the presence of distortion?
That's interesting.
That's the phase tensor, right? It's the phase tensor 1, 2, or 3.
Yeah, I mean it does. It does give you the dimensionality. I'm not really sure what you mean, I guess.
Yeah, I think what he means is, you showed that when you showed using the phase tensor, that depending on the threshold that you're defining your dimensionality of the data, whether it's 1, 2, or 3D at each frequency.
Yeah. I mean, yeah, it does show that you can do that. Yeah.
So Tule Kea Eken asks, says first, thank you, Alison, for a very fruitful presentation. Is there any limitation on the number of frequencies or sites or mesh size in the inversion? Another question is that can we apply the inversion for ocean data?
Yeah, I mean, these questions, I guess, are probably more about ModEm itself as opposed to MTPy. I mean, there's no limits. Well, I mean, subject to kind of, if you made a very, very, very large array, MTPy might struggle, but MTPy is not really limited in the mesh size. That's more like basically what ModEm can handle, or what the computer that you're using to invert using ModEm can handle. So I guess there is a limit, but I don't really know what it is, I guess would be the question.
Yeah, if you could hold that question, Tule, and ask it again in a few weeks' time when.
I've run about 300. I don't know. I'm trying to remember what I've run without any problems, but yeah, I think for number of sites, somewhere around 300 or 400 is what we've sort of managed to get to without running out of memory with ModEm. But yeah.
And now from Pierre Warzinac, fantastic job, Alison. Pierre was the one who gave the Razorback talk a few weeks ago.
Yeah.
Python-based processing thing. Cheers from the Razorback crew, Farid and Pierre. Did you create a phase tensor plot able to include a georeferenced map as background?
Yeah, you can. Yeah, you can definitely do that. The example I showed, it was basically it was just in lat long coordinates. So the net CDF was in lat long coordinates, and the model was the phase tensors were in lat longs. So you can provide it a Geotiff. There's another option. There's an example in the examples directory. That would probably be the simplest way to do that. Yeah.
And Pierre had a second question. Any plans to develop time-lapse data analysis modules?
I don't have those plans. I don't know about Jared, but yeah, we probably, I guess our next focus is going to be probably the V2.0 and kind of tidying things up a little bit more, and working with large MT surveys. That would probably be our next kind of focus area. Right.
Okay, is there any more questions for Alison? We've run out of questions. Please don't hesitate. No?
I don't know how to make this.
Okay. Oh no, there's Abbas has thrown one up. Thank you for your presentation. What do you think about the error in adding MTPy in the Anaconda environment?
What error is this?
I don't know. I'm not quite sure. What do you think about the error in adding MTPy in Anaconda environment? Sorry, Abbas, could you explain that a bit more? What do you mean? Which error do you mean? No. Okay, perhaps Abbas will get back to us.
Yeah.
Talia Alvarez asks, do you have any experience if it works well for marine data?
Well, I haven't really worked with marine data and MTPy. There's no reason why it shouldn't. Yeah, I mean, I guess I haven't tried it, so it'd be interesting to see how you get on. Let me know if you have any issues, because there's always things that we may or may not see. We don't use it.
Okay, well, thank you again, Alison. Absolutely wonderful. And as I mentioned to Alison before we came live, I actually downloaded this 2 weeks ago and got it running myself. I need to now use it. Let me just get the screen back from you, Alison. And whoa, there we are.
Oh yeah. So how do I? Yeah, you've grabbed it. Cool.
Oh, there we are.
Very good.
Right. Just wanted to say, finishing off, to welcome you all again next week. We have the Goldenberg at 17:30 UT, and I wish you a wonderful week. Please stay safe, and hope to see you in a week's time. Bye, everybody. Thanks again, Alison. Bye for now.